Hello, my dear students. Today we are going to discuss about design of tension member. Okay. So, first of all, think about it. Why do I have to design a member before construction? Let us try to understand with a simple picture. Suppose we have a tension member, we need to construct this member practically. So, if we do not calculate what should be the area of this section, if we select randomly any section, one can choose figure A, another man can choose figure B, another man can choose figure C. Now what will happen if we choose figure A? Area is very low. So according to the formula, if area will be low, area is low, then stress will be high. Our structure should not fail, number one. And if we choose this type of section, area is very high, so stress will be very low. Okay, structure will not fail, but the cost will be high. That means the construction cost will be high. So we have to keep in mind two guidelines, that is, structure should be safe to carry our design load, and the construction cost should be minimum. Okay, that's why to find out the actual cross section, actual minimum cross section which can carry our applied design load, we need some methodology or some assumption or formula. That's why we need to design the structure. That means we need to follow some method. Okay, so we cannot use this type of section because it will fail, and we cannot use this type of section because it will increase the cost. We have to choose this type of section, but how? We have to go for design. Okay, now when we are going to design a tension member, we need to know how can structure fail. The type of failure, number one, is cross section yielding. This is according to IS 800 clause number 6.2. Clause number 6.2, you can find the design strain due to yielding of cross section. That means cross section yielding is one failure criteria. And next is knit section rupture or fracture. Knit section rupture from clause number 6.3.1, we can see this is for plate, and another formula is for threaded rod and a single angle. So actual clause is 6.3. Design strain due to rupture of critical section. So knit section rupture is another criteria, and block shear failure is another criteria. That is 6.4.1, 6.4 design strain due to block shear failure. That means this is another criteria. Okay, you have to follow those formula to design a tension member. What is cross section? Cross section means total section. Suppose we are selecting a channel section or whatever you can choose. Suppose this is a channel section and we have to select this type of section. So total area of this section will be the gross section. Now what is neat section? Neat section is when we are going to design a connection, we go for bolted connection, we can go for welding connection, welded connection. So if we go for bolted connection or riveted connection, then we need some bolt or sufficient hole. So if we create a hole at particular area, then this area will be deducted. Suppose, try to understand this figure. Neat section means this thickness into this length, total length into thickness is that neat section. So for this case, neat section will be 240 into 8. This is the neat section, and this is the gross section. And neat section you can calculate by deducting this projected area, this area for hole, this area, this area. So in the figure, this red color, you can see these are the, if you add this plus this plus this plus this, you can find the neat section. And what is block shear failure? Block shear failure is like that when a member is subjected to a tension. Suppose this is the actual section. Okay, now if the tensile force exceed the strength at this position, design strength at this surface, you can see one line, here is a surface, and you can see another line, here is another surface. So in this surface, this part, this block will tear out by tension, and this part will tear out by shear simultaneously. So this block will remain at the same position of the connection, but this main member will tear out. This is block shear failure. Now before going to design a tension member, you need to practice some calculation of other parameter, that means which is AGAN or AG0 or AVG, ATN or AVN, like that. So before going to design a tension member, I am providing some calculation of effective area that you can, first of all you practice this, after that we go for design. The first problem is a 300 ISF 8 mm of grade Fe410, that is plate, this plate is used as a tension member in a lattice girder. It is connected to a 12 mm thick gusset plate by 18 mm diameter bolt of grade 4.6. Calculate the effective neat area of the member if chain bolting is done or zigzag bolting is done. This is chain bolting and this is zigzag bolting. Okay. Now for first case, this connection connection can fail by tear out along the one line. So we can calculate the neat area of this section. The necessary data is there for Fe410 grade of steel. Fy is equal to 250 ampere and Fu410 ampere. You know that dia bolt 18 millimeter. We are using 18 millimeter. Dia of hole, that is 18 plus 2 is 20 millimeter. Why we are adding 2? From table number 19 of IS 800, you can see table number 19, nominal size of fastener is, our nominal size is 18 millimeter, so 16 B to 22. So we can add standard clearance 2. Okay, 18 which is greater than 16, less than 22, so we can add 2. For chain bolting, the critical section will be 1 1. Critical section will be 1 1. Why not 2 2 or 3 3? Suppose this section tear out along the line 3 3. If it will happen, then the section will not fail, because along 1 1 and 2 2 the bolt will resist the force. Only 1 1 line is the critical, because if this failure will happen along 1 1 line, then total connection will fail. And this is the neat section. To calculate the neat area, we need this formula. What is this formula? Is coming from IS 800. Page number 33. This is the formula. An is equal to B minus NDH plus summation of P SI square by 4 GI into T. So this part is for zigzag or diamond bolting. Okay. So at right now we don't need this part, because our connection is in chain pattern. So this part is invalid for this case. So B minus NDH, B is 300 total width, minus N into DH. N is number of bolt. 1 2 1 2 3 4. 4 into 22. DH is 20. So 20. 4 into 20 into thickness T. This is 1780 millimeter square. This is the effective neat area for case 1. And for case 2, the section will fail or tear out along the line 1 2 3 4 or 1 2 5 3 4 or 1 2 5 6 or 1 2 5 8 9 10, etc. Please keep in mind, you don't need to think it with complexity, because if you create a diagonal line, obviously this is a hypotenuse, okay, and this is base and this is opposite. So hypotenuse is always greater than the opposite. That means when you are considering hypotenuse, that means already the length will be increased. That means effective neat area will also increase. So our effective neat area will be the minimum one from this. In zigzag bolting, the section may fail along 1, 2, 3, 4. 1, 2, 3, 4, that is straight line, vertical line. 1, 2, 5, 6, 7. 1, 2, 5, 6, 7. Only one diagonal line we are considering. 2 to 5. 1, 2, 5, 3, 4. 1, 2, 5, 3, 4. We are considering two diagonal part, 2, 5 and 5, 3. And 1, 2, 5, 8, 9, 10. This is another. This is also very long. Obviously, it will be it will not be the effective neat area because length is very high. You can see in the calculation. So our neat area formula is this: n is equal to b minus ndh plus summation of ps square by 4gi into t. And for first case, we don't have any diagonal line. 1, 2, 3, 4. Okay, so this part is also invalid. ps square by 4gi, this is also invalid. So b minus ndh into t is the formula. 300 minus 2 into 20, number of bolt 2, and dh is 20 into thickness t. This is the effective area for along line 1, 2, 3, 4. But for 1, 2, 5, 6, 7, 2 to 5 is one diagonal is there. That's why we need only one ps square by 4gi. B is 300, n into dh is number of bolt 3 to 20 dh, and for 2 to 5 one diagonal is line is present. That's why only one p si square. P is pitch is given as shown in figure, and 4 into gi is 75. For effective neat area along 1, 2, 5, 3, 4, that is 2, 5 and 3, 4, two diagonal line is present. That's why 2 ps square by 4gi are here. One is for 2 to 5 diagonal, and that is for 5 to 3 5 3 diagonal, 2 5 and 5 3 diagonal. Okay, so we are calculating, this is the value. And for 2 5 1 2 5 8 9 10, 1 2 5 8 9 10, diagonal part is 1 2 3, 2 to 5 5 to 8 8 to 9, 3 diagonal part. That's why 3 psi square by 4gi is there. 300 minus b is 300, ndh 4 into 20, and one is this is for 2 to 5, this is for 5 to 8, and this is for 8 to 9. Okay, so we are calculating some neat area, and the minimum of those 1 2 3 4, minimum of those 4 will be the actual neat area. So minimum neat area is at the section 1 2 5 6 7, that is 2032.66 millimeter square. Next problem: determine the effective neat area for the section shown in the figure. Steel is of grade Fe410 and bolt hole have been punched. Now for Fe410, Fi is equal to 250, diameter of bolt is 16, and diameter of hole is 16 plus 2 plus 2. Why plus 2 plus 2? You can see clause number 3.6.1 B2, 3.6.1, 3.6.1 B2. The sectional area of all hole in the section except for part in compression in case of punched hole hole size 2 mm in excess of actual diameter may be deducted. In case of punched hole, hole size 2 mm in case of actual diameter may be deducted. May be deducted from the plate. That means we have to add the hole diameter. That's why. And first 2 is coming from clause number table number 19. First 2 is coming from table number 19 and second 2 is coming from clause number 3.6.1. Now neat area of connected leg, this is connected leg because this is connected with the gusset plate, and this is called outstanding leg. This is connected leg, this is outstanding leg. So neat area for connected leg equal length of the connected leg minus dia of hole minus thickness of outstanding leg by 2 into thickness of the connected leg. We are calculating neat area of connected leg. That means this is the connected leg. So 100 minus diameter of hole, that is 20, minus thickness of outstanding leg by 2. That means thickness of outstanding leg is 10 by 2. That means we are considering up to this point where center line of these two legs meets. If I draw a center line here, suppose this is one center line and this is another center line. So we are considering up to this point 10 by 2, okay, into thickness. So 100 minus 20, total 100 minus 20 minus this 5, 10 by 2 into this thickness 10 is equal to 750 millimeter square. Neat area of outstanding leg, same, length of the outstanding leg minus thickness of the connected leg by 2, that means up to this point, okay, exactly midpoint of this two center line, into thickness of the outstanding leg, that means 10. 75 minus this 5, 10 by 2, this is 10, so this is 10 by 2, 5 into 10, this is 10, so 700 millimeter square. Neat total area is 750 plus 700, 1450 millimeter square. Since only one leg of the angle is connected, neat area will be reduced depending upon the number of bolts used for making connection. Further, since 3 bolts have been used for making the end connection, a reduction factor alpha will be used. According to IS 800 clause number 6.3.3, according to this clause 6.3.3, we are calculating the neat effective area where we can use this alpha. Approximately, when we are going to calculate approximate section, we can use alpha. The alpha factor is 0.6 for 1 or 2 bolt. When we are using 1 or 2 bolt, the alpha value is 0.6, and when we are using 3 bolt, alpha value is 0.7, and when we are using 4 or more bolt, alpha value is 0.8, and when we are going to use welding connection, then also alpha value is 0.8. So for our case, alpha value is 0.7. 7 because 3 bolts are there. You see 3 16mm bolts of grade 4.6. Number of bolt is 3. That's why alpha value is 7.7. So alpha into an 0.7 into 1450 is equal to 1015 millimeter square. This is the net effective area. And for this case B, there is no deduction for hole. Okay, that's why only hole will be you have to avoid. Net area of connected leg is equal to length of the connected leg minus thickness of the outstanding leg by 2 into thickness. That means again we are considering up to the midpoint of two central line. Total 100 minus this 5, that means 10 by 2, this 5 into 10. 100 minus 10 by 2 into 10. And again for outstanding leg 75 minus 10 by 2 into 10. So total 75 minus 10 by 2, total 10, and this is 10 by 2 into 10. And after that, by adding those two, 950 and 700, we are calculating 1650 the total net area, but we have to apply the alpha value. Alpha value is 0.8. You see, for welding connection, equivalent weld length for weld alpha value is 0.8. That's why 0.8 into 1650 is equal to 1320 millimeter square. This is the net area. And this is the next problem. Determine the effective net area. Now you can understand why this thickness by 2 is deducted from for both cases. You can understand in this problem. Determine the effective net area for the length for the angle section shown in the figure. The angle are connected with 18mm diameter bolt 4.6 and the steel is of grade Fe410. Here there is no one is outstanding leg. Okay, both are connected leg. So actually what is happening, we are considering this angle section as a plate. How? By rotating the another part 90 degree with respect to the point, that is the midpoint of the center line. Midpoint of the center line. About this point, we are rotating this part, another leg, and we are creating a plate-like element. After that, we are calculating the net area. For Fe, we are considering first case Fe410 grade of steel, bolt dia 18 and bolt hole 18 plus 2 from 19, table 19 you can see. For first case you can see this is 100 and this is 75, and where this is the rotating position, 90 degree rotation is here for this 75 angle length, and we are considering this as a plate. So total length is not 100 plus 75, total length is 165 because there is an overlap portion of 10 millimeter. Since the both leg of the angle are connected, for calculating the net area of the angle section, the outstanding leg of the angle may be rotated and total section may be visualized as a plate. We are considering this as a plate. Okay. Now width of the equivalent plate is 100 plus 75 minus 10, that is 165. 100 plus 75 minus overlap position, that is 10, total 165. And neat area along path ABC, you can see ABC, that is along the path ABC, there is only one bolt and no diagonal line distance is there. That's why you have to consider only B minus and DH. B is 165 and a number of bolt is 1 and DH is 20. So 1450 millimeter square. And along the path ABDE, one diagonal is present here. So PS square by 4GI will be there. So B minus NDH plus PS square by 4GI for one diagonal. P is 55 and G is 95, also present in the figure. G is 95 and P is 55. So this is the area. So the minimum area will be the neat area will be, actual neat area will be the minimum of AN1 and AN2. AN1 is 1450, AN2 is 1329.60. So actual neat area is 1329.60. For case B, this is case B, and again we are considering this is as a plate element. By rotating the other leg 75 millimeter length with respect to the point, that is the midpoint of center line of both angle, like this. And G is equal to, gauge distance is equal to 75. This is the distance. Width of the equivalent plate 190, and neat area along ABCD, that is vertical straight line, B minus NDH into 2, 190 minus 2 into 20 into 10, and neat area along ABEF, one diagonal is there, that's why 1 PS square by 4GI will be there, 1 PS square by 4GI. So AN2 is 1625 millimeter square, and neat area along ABEGH, two diagonal is there, that's why 2 PS square by 4GI. Okay, neat area is 1508.33. So minimum of AN1, AN2 and AN3 will be the actual neat area, that is 1500 millimeter square. So I stopped here. From the next video we start from problem number 4. Okay, thank you.